very clear when you go to experimentation. So this is the DS1104 module we have at present in the lab. One is a control card which is there, which is inserted in our CPU. This control card we are taking out, and this is the connector panel which is there in our side, and this is the license dongle. Without this license dongle, it will work. Unless any license if you are procured, that you have to insert, then only it will work. Otherwise, it won't work. They will provide it's like a license set, physical license, right? Not virtual. So if we see the specifications of what this controller having, one thing is much important. You have ADCs of 16-bit, 4 ADCs, 16. Remember, normally you will get 12-bit ADCs, but here we have 4 ADCs of 16-bit and 4 ADCs of 12-bit. Total 8 ADCs. Total we have available 8 ADCs. In that 4 are 16-bit and 4 are 12-bit. So whichever is comfortable, you can use it. And we have 8 DAC pins, DAC output available. 2 incremental encoders. Onboard independent 64-bit floating processor is there, 64-bit processor. Onboard master-slave concept is there. You know what is master-slave. 2 processors will run parallelly, master-slave concept. And we have other digital I/O pins which are there. We'll see the configuration of digital I/O pins. And we have PCI development board, I/O breakthrough board, control desk software, what available in. Along with this hardware, they are given one software, that is the control desk software, and MATLAB. MATLAB is anyhow we are using. Along with the MATLAB, control desk, and these devices we are going to operate. This is the whole package. MATLAB, one software, is the generally we are using. Control desk is to these people's design software, and along with this hardware. This is our has a package of controller. Right? So, of course, it is very sensitive device. We need to be taken care of some safety precautions. What safety precautions? Definitely. The board has to be handled with care, grounding. It should be first properly grounded supply. The basic care is the neutral or grounding. It should be properly done. Otherwise, our European standards, you know, it is not designed for Indian standard supply system. It is designed for European standard system. Normally, neutral voltage should be less than 6 volts. Imbalancing thing. Normally, in India, it will maintain about 12 volts. Our neutral voltage, it could be about 12 volts, right? So that's why all errors will come if any European system if you install here. Some errors are some damages will happen because of our standardization. Their standards are much more specific. Our standards are very liberal. Our system will be liberal. That's why most of the time you will find a problem. And second precautionary thing is it should be operated with UPS. The supply which is given. Other things are very normal. Only this will be much more important part. Now, how you have to start your platform? First, initiating point is your MATLAB only. We have to open the MATLAB, and already the package will be installed in the MATLAB while installation process only. No need to do anything. They will install while in the installation process. Once installed, once you open the MATLAB, such window will be comes into your MATLAB immediately. If you open the MATLAB, automatically this window will come. In this window, what is there? We have to select which model we have. They have different models in their packages or hardware setups. Which model we have opted, that model we have to select. Here 1104 is our model, or 1202 is another model, the updated model we have. That will also be reflected. We will see that. We have to select this model, then only the package will be activated. Their packages, their libraries will be activated. This is the library activation process step. Once you select, in the MATLAB environment, that library package will be activated. That is the step number 1. Once that is there, this is your block model which is available, which is already installed in your DSpace Simulink package. Right? So you can check here. DSpace, this is showing 1103, 1104. Any model, which model you will have, that package module will be available. Now in this, what will we have? These are all your components. This component will be available. Which component I have to use it? That will be taken, selected, drag and drop to your Simulink, connect it. We'll see the example how it will be. Only thing, like how MATLAB, all components will be there. This is also a component, like a Simulink block set. On that some flexible modules or some content will be available. We have to drag and drop to our simulink and we have to use it in our requirement level. As Monty explained, to set some settings for that operating of our box. The settings will be, it should be a fixed step, ODE1 Euler, your solver should be ODE1 and step time should be infinite. Because in simulation you can define the time, but in real time your time is infinite. It has to run continuously. So that conditions you have to run infinitely. Right? Otherwise, if you give 10 seconds, the pulses will become only 10 seconds. It will stop. In simulation it is okay, we will store the pulses and we will see later. But in real time, the 10 seconds goes, pulses will also go. That condition will run with infinite. These are the fixed settings for any board when you are operating. Infinite, fixed step, ODE1. This is the setting of your configurations we have to maintain and another setting. This is our connector, outside connector. It will be visualized like this. Our board is there, you can see it's like a box. In that box, what will be there? So we have certain numbers you can verify, CP19, CP20, CP22, 21, 18, 17, something. They are given numbers. So according to that, acknowledgement is given. You can see CP1 to CP16, CP1 to CP connecting point. CP means this is just a connecting point. CP1 to 16 is a BNC type cables. BNC cable, long type cables. What will be there? You can see 1 to 18, some ADCs will be total 8 ADCs and 8 DACs, total 16. These all BNCs consist of composition of ADCs and DACs. 8 ADC pins, 8 DAC pins. And we have master and slave digital I/O pins, right? So you can see CP17 and CP18 is the master and slave connectors, which are the digital I/O pins, which are how you can use it, that will be used. Master connector is CP17 and slave connector is CP18. Right? And remaining is you can see incremental encoders and interface connectors, RS232 will be there, and that is for communication purpose. The other ports will be there, that is for communication. Our major is these I/O pins, ADCs and DACs. Right? There will be more concentrated. And of course, if you need any communication to other devices, you can take it in communication ports. Right? All types of communications will be there. This is general way of visibility. Then CP1 to CP16. What could be your numbering? You can see CP1 to CP8. CP1 to CP8. Those are ADC 1 to ADC 8. Numbering is fixed, prefix. In MATLAB also you have to use. CP1 pin is ADC 1. It will be mapped when you are using in the MATLAB. First ADC you have to map with CP1, that is ADC 1. Right? So like that you have to connect it. And sometimes CP9 to CP16 is DAC from 1 to 8. It is the DAC pins. Right? 8 DAC pins, 8 is ADC pins. 8 the prefix circuits. And of course in that 4 are 16 bit and 4 are 12 bit. ADCs. Particularly ADC is much more important to us because when you measure any speed signal, voltage signal, current signal, anything, how accurately you are measuring depends on your ADC bit count, right? So 16 bit is much accurate level of measuring. Mostly, generally we use 12 bit, but 16 bit is okay. It will be much more accurate, considerable ADC. And CP17 is the master I/O connector. Master I/O connector, you can see the I/O pins and grounds which are available. What we use, these pins we use it as an input pin or output pin, digital information only. What I can say maximum, I can give either digital information as an input or I can take a digital information as an output. That is your choice. How to use that pin is your choice. But it should be a strictly digital information only. If you want any analog information, either ADCs and DACs you have to use it. Otherwise, your information is purely digital, then you have to use it this either CP17 or CP18. CP18 is also a, and one more is there important, this PWM module is ready-made module available. Right? So you can see the PWM pins. How many will be there? You can count 7, 8, 9. There will be some 8 to 10 maybe exactly number of pins are find out. 8 to 10 ready-made. We have block set of ready-made PW model. No need to write. See, earlier he has done FPGA. What he has done? Science modeling he has done. Comparison some code he has done. Here nothing will be there. Just one block will be there. There carrier frequency you have to define. You give the modulation index. Automatically pulses will generate for your 6 pulses. Oh. And dead band is inbuilt. What is the advantage of that one? The comparative action module is already predefined. What is the inside inbuilt module means what is it? Whatever the action, only you give the input, you take the output pulses. Remaining all action is predefined, already pre-written, right? So that could be the advantage. So you can use it directly if it is required. Otherwise, you can write your own. You can select your own sine wave. You select your own carrier wave. Compare it in MATLAB. Then what? Individually also you can do it. Your flexibility is there, but you can do that, right? So how it will be works? Obviously, this has the interface between simulation environment to real-time environment through ADCs and DACs, DAC and ADCs. So this is one type of your. This could be continuous section, continuous time period, and it is a simulation time. Both has to be interfaced. When you understood this one clearly, the time difference is there. The simulation time and real time is not same. That you have to understand. Your simulation time might be anything, but real time is the real. Right? Now we are going to interface this. Isn't it? In simulation, 10 seconds is not 10 seconds. 10 seconds we are defining for 10 seconds. That is not a 10 seconds. It may be a sometimes 1 hour. 10 seconds time it will run for 1 hour, depends on your complexity. But in real time, 10 seconds is a 10 seconds. Now we are going to interface these two. That issue you have to be sorted out, right? So otherwise, your real time is work on 10 seconds, and the simulation environment will work for 1 hour, and result will come after 1 hour. Where is this 10 seconds? It won't work, right? So that problem will be always be there. That has to be synchronized your real time with simulation time. You have to maintain always your real time with. We'll see how it will. That's what I'm saying. How much your response time your simulation. Morning we have discussed that sample time. How much quickly it will respond. So it will decide your synchronization between simulation time to real time. Simulation time to real time. So you can see, if I design my program, this will indicate. If I design my program within my sample time, your time synchronization will happen. Your time synchronization will happen if you are design your program within your sample time. Sample time, what is the sample time? How much sample time you have selected, the limitation of that sample time for the controller. If your program is within that boundary of its computation, then it's fine. It will be synchronized. If it is not designed properly, if you have designed very complicated system, then what happens? This computation time will be overlapped in the next cycle. It will take a long time to process it. Obviously, it will generate the error. That's what the error is. Mismatch between the simulation time and real time. Mismatch between the simulation time and real. That is the error. Right? Obviously, I have to be taken care of this when you are operating any controller, not only this one. This will be a general concept. Wherever you are going, any controller you are selecting, you should have your computation time should be less than sample time. What is the time which you have selected? That care has to be taken. And of course, ADC, if you see it will convert from your analog to digital data and it will take it to simulation environment. Particularly this environment, if you give 10 volts, the limit is from plus 10 to minus 10 volts for ADCs. You can give plus 10 to minus 10. Most of the controllers it won't accept negative voltage because it will accept only plus 3.3 voltage. Then that condition, what you have to do, you have to do signal conditioning. Entire negative part also you have to shift it to positive. Again, when you analyzing, again you have to do signal conditioning, signal shifting, signal conditioning. So many things you have to apply when you are. But this controller having a negative 10 to positive 10, you can apply even sine wave with the negative voltage to positive. Right? So that flexibility is there. And one thing you have to observe, if you give 10 volts in the real time, in the simulation platform it will give 1 volt. It will give 1 volt. Then what I have to do? I have to multiply with the 10. The real value will come into the simulation. Right? Always ADC you have to multiply with the 10. Always you have to multiply with the 10 because if you give 10 volts inside it will give 1 volt. to make it into equivalent value, you have to multiply with 10. That is the first point to the ADC. Coming to DAC, it's a reverse operation. Reverse operation. If it is a simulation, DAC means from the simulation to you are taking outside. That your digital information you are taking as analog information. In that terms, what will happen? In the simulation, if it is a 1 volt, outside it will come 10 volts. Equivalent, you have to divide with the 10. Right? You have to divide with the 10 to get it realistic values. Because 1 volt, here 10 volts is equivalent to 1 volt in the simulation. Right? So that has to be worked out. So that is very basics which is required. We will see what could be done for this simple temperature control. Morning we have discussed. It is not meant for temperature control, but we will see example what could be. Set point, I have suppose I want to fix some temperature, 30 volts or 30 Celsius or whatever it may be, you set some temperature. Ultimately you measure the temperature, your controller will be have to set up. That is simple closed loop operation. What I have to do? To close the lamp, that is the power. Analog output you are giving. Now what temperature sensor is measure the temperature from the lamp. That will be given to ADC. If you take the analog power and it will convert into digital. And my logic I write it, whatever it is your controller, P controller, PI controller, whatever you want you control. But ultimately it will generate control signal to control the temperature to reference point. Right? So this is a simple process of your closed loop what you are doing. This is entirely your DS1104 will do. Because these ADCs are inbuilt, DACs are inbuilt. Only sensor you have to take it from the sensor plus or minus 10 volts you have to take it. Equivalent of temperature, give it to that one. Design your logic of your closed loop and output value will be set. It will be settled in the closed loop and lamp temperature will be controlled. Same thing will apply to any component, right? So we will apply motor, we will apply to any process. Same thing will be done. Sensing elements will be more, right? So voltages, if you are taking 3-phase, I will take the 3-phase voltages. Currents, if you want to take the 3-phase current. We will see what could be one more example you can see. What is the same example, right? So what is the temperature one? You can see. Set point is 20. Set point is 20. ADC, we are measuring our ADC. As I told, it has to be multiplied with 10. It has to be multiplied with 10. Always ADC has to be multiplied with 10. And your DACs will be divided with 10. You can see at the end point, DACs will be divided with 10. And this is multiplied with 10. And your logic will be whatever it is, you do it. Remaining, I am not discussing what is your logic. Your logic is your prospect. Only thing, how you will take the information, how you will give the information outside. How you process the information, that is your research. How you process is your research. But we are, how to work out with that controller, we will check it. Right? So this would be an example what we discussed, the circuit project. And of course, you can measure that temperature, how much it is there. You can measure from the DACs, one more DAC, and the digital information also you can take directly. Analog information you can take. Digital I/O also you can take the digital information. What is my temperature in digital form? You can take it master bit output. What is that? Similar information it will be decided. And if I apply the same thing to my any device we are in the motor, what is the motor? You can see it is a motor generator setup. Motor generator setup. What will be there? My power electronic board is there. From that, you can see that is a 1104 board. This one is your 1104 board. And this is your power converter circuit, and this is your motor. So we will connect your power supply from the power connector, and input voltage will be there. What I will measure? I will measure the current. Input, I will measure the current, input voltage. And from the encoder, we will measure the speed. We will measure the speed. And based on these two information, I can process in the computer to generate my PWM pins. This PWM will be given to my converter, and your converter will provide the sufficient control. That is only we are doing it, right? That's what. How much you are applying? That you can apply. Only thing your machine and process changes, but right, it will be the same. One more, sine wave generation. Yesterday he made it in FPGA samples, so many samples, 255 samples he made it. So in MATLAB simple one ADC, one DAC you can generate it. In FPGA, we have to write some samples. Same thing, amplitude and frequency. Write your equation in MATLAB. Take it into DSP. Generate digital information. At the DAC, you can observe your sine wave. Simple with MATLAB, you write your sine wave. You take it as sine wave, whatever you design outside. Whereas FPGA, you have to design in code. That is the basic examples. As I mentioned, control desk environment, why it is needed. MATLAB we are designing, if you run it, actually this is not required. If you want to run a fixed program, this is not required. But I will tell you the difference. The same MATLAB interfacing can be done by any controller. I am not saying this is only the controller we can do. And I told Arduino can be done the same. Morning also we discussed. Arduino also flexibility. Arduino 232 bits with free of MATLAB, you can do the same. Whatever the part one weight is there, the same thing Arduino also doing. But what is the advantage? Why we have to do this one? The difference is in the Arduino, once you write a program, other controllers, what could be? Once it is fixed, you cannot change any variable. If you want to change the variable in the runtime, what you have to do? You have to run the program again, and you have to build the program again. You have to dump the program again. In regular any controller which is there. But here, they have provided such an environment, the control desk environment. You can control your variables during the runtime. During the runtime. Whatever the variable, suppose my sine wave, I could have taken my sine wave. Here this amplitude and frequency, with the previous values you run first, no need of control desk environment. Sine wave will generate with these values. In the MATLAB, whatever the values you have given, it automatically runs. What difference will make? You open the control desk environment. I want to change 58 to 60. During the runtime only can change. That is not possible in other control environments. Only possibility in your this control desk environment within this case. That is the advantage, because most of the cases where you want to change your variable during the runtime. Otherwise you have to stop the process and you have to change the variable name or variable value. Again you build it, dump it. Again it takes some process. Delay. So that will be avoided. That's why they introduce this. And I can observe my variable changes in the display of control desk. I can measure my speed, I can measure possibility variables